and sea series no. 39 nautical stability in aeroplanes W. LS Mater Co. ID. Page 2, page 3, page 4, natural stability, page 6, page 7, page 8, natural stability and the parachute principle in aeroplanes by W. Lemaitre Roman 4 Hahn. Sec. Aeroplane Building and Flying Society with 34 illustrations Zahn and on E and FN Spawn, Limited. 57 Haymarket Mu J2 Odd. Spawn and Chamberlain, 123 Liberty Street, Ikiai. Page 10, Contents Frontispiece. Roman 4 Preface. Roman 9 Chapter I, The Importance of Stability. 11 Roman 2 Speed as a means of stability. 14 Roman 3 The Low Center of Gravity. 17 Roman 4 Short Span and area. 28 V Variable Speed and the Parachute Principle. -36 VI. The design which fulfills the conditions 39,274,247. Page 12. Preface. Since there is nothing new under Thesson, it is useless to pretend that there is anything new in the design here advocated orthotheories advanced. Both are rather their salt off a common-sense consideration of the different points off of flying machines, natural and artificial, and an endeavor to select from the great number of good points those which see most likely and toge into practica machine. The conclusions reached are the result of a quite independent investigation, carried on over 3 years by means of numberless experiments, and the writer has endeavored to make no single statement which he cannot by some experiment amply prove. Page 14, Natural Stability in Aeroplanes, Chapter I. The Importance of Stability. In considering the whole question of aviation, it becomes evident that the point to strive for at the present juncture stability. If we're ever to have a practical flying machine, that is, a machine which we can see sweeto yacht, a motor car, or a bicycle, it must be on that we can trust to keep its balance by reason of the natural forces embodied in it, and without any effort of control on the part of the pilot. It may be objected that a bicyclito's not dothise, and this is true, but on the other hand, the upsetting of a bicycle is a small matter, whereas the tilting off an airplane mostly means sudden death to its occupant, and it is probable that if the somic consequences followed the tilting off a bicycle, bicycles would soon have been made with 4 wheels. At present, aeroplanes are the most unstable of all things. The least gust, the least shifting off weight, natural /s, stability in aeroplanes, the slightest difference in the density of the strata of the supporting air, and the machine sways, and if not instantly corrected by the pilot, this way becomes a tilt. The tiltative and the rest is silence. The first aeroplanes, the Wrights for instance, were soundstable that 20 minutes in one of them was as much as most iron-nerved man could stand, the continual strain being too exhausting to keep up for an length of time. Throwing out extensions and outriggers in all directions, we have altered that to certain extent, butanliton extent we have not ecatrid off it. The monoplane is probably the most unstable, as might be expected from its smaller surface, but the biplane runs it pretty closely, and the difficulty seems to arise chiefly from the fact that the machines are built round the propeller. In the case of a Tora car, the machine is built first and the propelling means is fitted on a sanaxil lyre. The consequence is that an airplane, which is safe enough while the propeller is exerting attractive force of some 250 ibs, becomes, the moment this power is for any reason stopped, merely a shapeless construction at mercy of the and the force of gravitation. It is true that most machines may be made to glide if the pilot is clever enough and quick enough to steer them into the proper gliding angle. But the machine that will naturally and by reason of its design assume its proper gliding angle when the propelling force is withdrawn has not yet been built. Such a machine would have natural stability. Importance of stability 13. It will be recognized that this natural stability, which depends on the design of the machine, is something entirely different from automatic stability of which there are many systems, all having this own defect. That depending upon working devices, able planes, gyroscopes, compensating balancers, pendulums, etc. They are all liable to go wrong and refuse to the moment a sudden strain makes their perfect action most important. Considering that the propeller is the inline means the aeroplane has of keeping in the air at all, the question arises, is it possible to design a machine that will be stable to the extent of descending safely when the propeller stops, and that will yet be good and speedy flyer? That is the problem we have to solve. 14. Natural Stability in Aeroplanes, Chapter Roman 2. Speed is a means of stability. It is recognized on all hands that speed is a great factor in the problem of stability. To begin with, a machine going at high speed would be practically untouched by gusts of wind, different densities of air strata, holes in the air, etc. Also, its greater momentum would tend to keep it in a straight line, not only relative to its course, but also relative to itself. That is to say, swings being started in a horizontal plane would tend to keep in the summit plane and would not ease a little to sway out of it. Both these effects of natural law show that a high-speed machine must be more stable than a low-speed machine. How then add to design a high-speed machine? Leaving aside texture of higher power, the first point that suggests itself is to lessen the head resistance. All fast things, boats, birds, arrows, even motor cars, are made long and narrow. It will be objected that abord with its wings outspread is not long and narrow. But in the sense in which this illustration is meant, the bird swings, being merely its propelling apparatus, done account, and when the bird is at its fastest, asynthesu pafahawk oren. Beta means off stability 15 eagle. The wings are shut at lithebdisosto offer nor assistance toits lightning passage through the air. If we're at to follow previous experience in nature's laws, our aeroplanes must be considerably reduced in span. To drive through here at a high speed with a machine of 40 footspan is a practical impossibility, both because of the tremendous power it would require and also by reason of the great strength the plane must have to withstand the resist ants off the air. In reducing thespan, however, reduce the lifting surface off the machine. But on the other hand, it must bear remembered that the lifting efficiency is increased by increasing the speed. Lift is the product of supporting surface and speed. A small plane driven at a high speed will give us great aliftos a large plane driven at a low speed. Speed, again, is the difference between the propelling power and head resistance, and we can increase the speed by decreasing their resistance. Follows, then, that we need not necessarily give you lifting power by reducing the span of the wings, since the shorter span gives greater speed, and the increase efficiency by reason of the greater speed would gotta make up for the loss off span. It is, then, quite possible to signa short span machine which shall be sufficient for lift as a long span machine, and which will have the advantage of possessing, by reason of its speed, much greater stability. L6 natural stability in aeroplanes, but the span is not the only factor in the speed problem. In the low-speed machines at present in use we have found it necessary to curve the planes to get greater efficiency. This efficiency is also gained at expense of head resistance, and it is already recognized that the higher the speed the less is need off camber. This is the same problem over again. A high-speed flat plane will give as much lift as a low-speed cambered plane, and we gain instability with every additional mile per hour. The third point considered in the problem of speed is the resistance, caused by the multitude of struts and wires, the body of the pilot, the tanks, engine, and all the other impedimenta, projecting in all directions from the body of the aeroplane. It has occurred to our builders that if the whole of these things could be collected together and enclosed in a light covered in carafa proper shape, the skin friction of such a car would be much less than the total head resistance offered by different obstructions so covered. There is another advantage gained here, for if, at 40 miles per hour, the force off the wind is very seriously uncomfortable for the pilot, the position at such speeds as 70 or 100 miles per hour would be quite impossible. After Roman 3, the low center of gravity. The first thing that occurs to the investigator on the subject of stability nature offers use as your means of keeping your machines upright by adopting the simple method of placing all the heavier parts at the bottom. In all other constructions we have adopted this plan with perfect success. In boats, yachts, cars, balloons, everything man uses in fact, the simplest, bestand most obvious method of keeping anything upright is to utilize the force of gravity. Place the lighter or supporting parts above and the weight below and the thing is stone. This simple method of obtaining stability did not escape the aeroplane designers, and we have had several machines which embodied this principle, more or less. Unfortunately, however, they all proved failures. A machine would be designed, and with weight high would fly well, though it wasn't stable. Put weight low and diaugatrid off the instability, and at the same time the machine became unmanageable. It looked as if flying and instability were interchangeable terms. So as it was a machine that would fly the designers were after, weight was B. Natural stability in aeroplanes kept to pan the stability was left to thep a lot. The machines were made sensitive, acidiscold, that is to say, sensitive to touch off the rudder or the balancers. They are also, it is true, equally sensitive to gust off wind or a slight shifting off wind or pressure, and this has caused the smashing off a good many machines and some pilots. But after all this is the fortune of war, and noon is compelled tagup in an airplane. The curious thing about it is that it does not seem to have occurred to our designers that, if their pet design would not fly with weight low, perhaps it might be possible to alter the design instead of altering the position of the center of gravity, and subtain what we're looking for, a naturally stable machine that is yet sensitive to control. There are what chief difficulties in the way of low center of gravity machine. One is that the heaviest portion of the machine being some distance below its support, it is apt to give rise to pendulum or swaying motion. The other is that off tilting or banking up in turning a corner. These are really two developments of the same difficulty, i.e. pendulum motion. If we take a strip off stiff paper to present a plane and putasmal weight in the center off the plane, the model on being glide toward does not tend to sway fig. If we put our weight on a tiny piece off wire and ensure so blow the plane fig. 2. And set the model free, it will probably acquire a low center of gravity 19 swinging motion as it descends. That is the whole trouble. The trouble is real enough, but the fallacy isn't supposing a tobel theffault off the low center of gravity. All ships that were ever designed have a low center of gravity, yet some roll dreadfully and others do not, which in itself should be proof sufficient that it is that assign off the machine and not position off the ballast that is at fault. Let us note some experiments. It will notice that in the machines which have employed Fig 2, Fig 3, the low center of gravity thespan off viewings has usually been 30 feet or more and the center of gravity about 6 feet below the center. Here is a paper model off the present aeroplane Fig. Here is the Sama machine with allo center of gravity Fig 2. Now bend the paper upward in Fig 3 and yaugatrid off the swaying. Also, of course, yaugatrid off the supporting surface. But there is probably some point off greatest deficiency where yau may compromise. If you take model 2 and bend it slightly, Fig 4, it will sway button it much, not so much as Fig 2, now B2. When natural stability in aeroplanes with a pair of scissors clipped doing a bit at a time, and yau will find that as thespan gets shorter, the swaying decreases. And that when yau have the 3 points formed by thenes off that wowings and the weight equidistant from the center where they meet, Fig 4, the plane stable Fig 5. Their asin is that itis not the pendulum with the weight at the bottom that swings so much, but the long wings that seesaw. By shortening thewings yau have reduced the length of the seesaw, just the sameas reducing the length of the pendulum, and consequently, by pendulum law, the oscillations must be much quicker and shorter and will atone to damp out. It is curious that this point seems to have escaped the designers. It is well known that all pendulum motion tends to damp out, and the shorter the pendulum the quicker it comes towards. Hitherto thady has been to shorten it vertically. Low center of gravity 21, but the same effect exactly is obtained by shortening it horizontally, and the low center of gravity remains to give stability. It was stated by some sapient objector to the low center of gravity that the pendulum motion once set up increased till it in the machine over. A pendulum which increased its swing gate every stroke would be something new in the scientific world. Another development of the pendulum difficulty is the probable fore and aft sway. This may be overcome by increasing the supporting surface off the tail. Many machines do not lift with the tail at all, or those that do employ lifting tails haveth them with very small surface. Consequently, the center of gravity comes nearly under the center off the main plane, and the whole machine, turning on its center off gravitational directions a sauna pivot, is liable to swing fore and aft. The supporting surface off tail be increased and the center off gravity carried further aft. This pendulum motion is also rendered impossible, and the machine is stable both ways. Of illustrations may serve to make the advantages off the low center of gravity more clear, and to avoid complications we will suppose the plane stobe stillend in still air. Let Fig 6 represent an ordinary flat plane having its center off gravity coincident with its center off pressure. The center off pressure fetch half or wing being at AA. The plane is equilibrium. Now allow it to tilt, Fig 7, and it will be seen that it is still in equilibrium since the weight is in the center and thewing tips equidistant from it. 22 natural stability in aeroplanes let it tilt still more till it is vertical, Fig 8, and the balance is still the same. It is evident therefore that such a plane would travel equally well in any of positions shown, and that it can only be kept in posi on Fig 6 by the skillful manipulation of the pilot, Fig 6, a Fig. In the same way, the machine having no lifting tail is longitudinally unstable for being balanced on its center off pressure, which would be coincident with its center off gravity and probably about 2 feet from the trailing edge of the plane may assume any position. Figs 9, 10, i.e. in 12, and still be in equilibrium when it is evident that the proper position, low center off gravity, Fig 9 is only maintained by the constant control of the tail elevator. Now take the case of a machine having a low center off gravity. Its natural position is shown at Fig 13, and it is at once evident that any other position such as Figs 14 and 15 could not be maintained Fig 9, Fig Roman 2, Fig 10, Fig 12, Fig 13. For a moment, since the 8 being at an angle, must inevitably drag the machine back to its natural position, Fig 13. In the same way with regard to longitudinal balance, a machine with 12 lifting surfaces such as Fig 13 is in its natural position with the center off gravity perpendicularly under the center of pressure. Any other position such as Fig 17 a ism 24 natural stability in aeroplanes possible, as the gravity pull must drag the machine along the dotted line till it resumes its proper and natural position B. The next difficulty is in the banking gordleting caused by the turning off the machine and going round a curve. In every interesting discussion carried on Fig 14, Fig 15. In the Aero, it was stated that a low center of gravity machine could not bunk up, as off gravity acting on the low weight would prevent it. It was also stated by an author writer that the machine would bank up too much and slide down sideways, because the greatest weight having the greatest momentum would swing out too much. There is a low center off gravity 25, evidently some confusion here. Let us consider the question. In turning their aero 3 forces todake and talk consideration. 1. The centrifugal force, which tends to make the machine fly off at a tangent curve at which it is turning. 2. The action of gravitation. //T7/T7B Fig. 17. 3. The extra lift given by throwing on the outside off the curve, owing to the fact that it travels faster through air. The centrifugal force acts strictly in proportion to theme as it acts on, but at his at time it must be remembered that the greater force acting on the greater mass haste the greater mass to move. That is to say, that if the top part of the machine was free. 26. Natural stability in aeroplanes light and the bottom part very heavy. The force acting on the light part would be sufficient to send that part swinging out when rounding a curve. And the greater force acting on the greater mass at head bottom would be sufficient to send that out to exactly the same degree. Consequently, if only centrifugal force is considered, the whole machine would swing out without any tilting at all, retaining its upright position. But we must take another factor into consideration, their resistance off the air. This resistance would be greater on the greater surface off the light top part than on the heavy bottom part, and consequently the bottom part would automatically swing out most, giving the bankage effect. This would be increased by the extra lift given to the outer wing by reason of its greater speed. If we then take the force of gravitation into the problem, we shall see that we have factors unequal speed and unequal air resistance tending to bank up the machine, and on force of gravity tending to pull it straight again. At a certain angle due to the amount of force exerted by each of these, the two opposing factors would balance, and the machine would be in equilibrium. It would appear that most of the difficulties connected with the low center of gravity machine areth result of hazy thinking and slipshod reasoning, and that the don't exist in fact. And let it be remembered that the low center of gravity machine with short span has not yet been tried except by the writer, who has succeeded in making a paper model on thighs. The low center of gravity 27 planturn in its own length without in any way losing its stability, swaying, banking too much, turning over, sliding sideways, or doing any of the frightful things which some people declare it must do. What it does do is to recover its balance though started from the most impossible positions and always land on its feet. 28. Natural stability in aeroplanes, chapter Roman 4. Short span and area, both on account of speed and also on account of stability, with a low center of gravity, where forced in the direction of the short span machine. How to construct a machine with a span short enough to damp out swaying and yet with sufficient lifting surface to raise the machine and its load. The position is somewhat simplified, as already pointed out, by the fact that thought lift is decreased by the decrease in span. It is to a great extent compensated by the increase in speed. Also, another compensation is offered by the fact that fore and aft stability requires a lifting tail. Lift is largely in proportion to the length of entering edge of the plane, but it does not always follow that the entering edge must be at right angles to the direction of flight. The done machine obtains its lift with an entering edge at entirely at an angle of some 45 degrees, and it should pay exact replica of their head off prehistoric man and paper darts offer school days, a death sign, by the way, that was patented in 1860. At first sight it would seem that the lift in airplane. Short span and area 29 shaped this, Fig. 18 would only be equal to the lift given by airplane with an just longest distance between on C, thus Fig. 19, but this is not so. All thought lift is not so great as it would be if edge was straight and on a line, Fig. 20, it is very much Fig. 18. Greater than it would be on Fig. 19. The probability is that it is about halfway between 19 and 20, but probably nearer to 20 than 19. There are no exact data to goon, but the efficiency of the done machine would seem to show this. Fig. 19, Fig. 20. Again, in seeking for planes that offer the least resistance to the air, one of the best that suggests itself is T-shape, Fig. 21, and this may be improved by cutting off useless corners, Fig. 22. A plane of natural stability in aeroplanes, this shape lends itself to great strength of construction owing to its small extending parts. It is compact, it gives an entering edge a fast long ag asset span, and gives a lift in proportion to the edge, and it is in /7 Fig. 21, Fig. 22, itself stable. Having thus evolved a suitable plane for the front of the machine, the best thing to do is to base the back plane on the same design, and joint two planes to their to form the supporting surface of the machine, allowing sufficient space between them Fig. 23, to avoid any interference or overlapping. The design then stands thus, Fig. 23, when the back plane is a slightly smaller copy of the front one. The position of the center of gravity in this design would be coined. Short span and area 3, sident with the center of pressure longitudinally and laterally and would be situated about at a paper model on these lines with a low center of gravity may be easily constructed and will prove useful in illustrating the different points here stated. The paper Fig. 24, v Fig. 25, should be cued out sufficiently wide tolo off a central longitudinal fold, Figs. 24 and 25, and a roll of paper should be made for ballast and pushed through the fold as shown in Fig. 26 at head point marked A, Fig. 26. The writer, when exhibiting at Olympia this year, distributed 500 off these paper models, and the almost uncanny way in which they righted themselves when started from all sorts of impossible positions greatly. 32 natural stability in aeroplanes interested the visitors. In fact, numbers of persons spent considerable time and ingenuity in trying to force the little glitter to turn over Ordiv, but quite without success. In order totes the turning capacity off this design, a rudder should be fixed to the tail, and the model launched at a moderate speed, when it will be found that it turns quickly and without any pendulum motion, and without any perceptible tilt. And although the writer's experiments with the paper model and with many larger ones on the summit plan have run into thousands, none of the models have ever been induced to come down in any other position but in their feet. The largest model, which measured 6 ft, 6 in length, was launched both upside down and with its head pointing vertical toward from a height of 30 ft, and in each casserrighted before it reached the ground and landed on its skids. A safer their lifting surface. Very simple expedient offers itself in the shape of a duct built on the box kite principle. A diamond-shaped box has been proved over and over again to be a very efficient lifting device, but it has not yet been tried on an aeroplane. Fig. 27. It is also a great stabilizer, since the entering into the diamond-shaped open and just collected and compressed into the top angle there, and the whole box is thus practically suspended from its apex line in absolute stability. The lifting efficiency of such a box, or rather that a portion of box, for the bottom part is not needed on a machine, is short span and area 33 lc. 34 natural stability in aeroplanes considerably greater than the value of the entering edge, and different the whole length of the machine, it forms a triangular girder of great strength, giving rigidity to the whole structure. The lifting efficiency is doubled by allowing the center third of the girder to open, as that air from the front part escapes, and the back part forms a wintering edge. There is also another lifting factor to be considered, and this is the car. If the car is formed with a flat bottom, Satansa becomes an efficient lifting plane, and if the car is suspended with an open space between it and the under surface of the plane, the loss caused by the negative angle of the proportion of the car front is compensated for by lift given by the deflected air the under surface of the main plane. See Fig. 28. It will be recognized that in the design her being gradually evolved, the great lifting surfaces of ordinary machine have not been largely reduced. They have simply been broken up into several smaller surfaces, each of which retains its efficiency. Think of the sum and nature happened in prehistoric days, when our first navigators at last made up their minds to abandon the flat-bottomed raft with its huge supporting surface, for the newfangled and dangerously narrow boat. When all the different surfaces here mentioned are taken into consideration, it will be found that the lifting surface in a monoplane machine off this design, with a span of 20 feet, ice qual to the lifting surface. Short span and area 35 off an ordinary biplane with a span of 40 feet. And as head resistance less than half that off a biplane speed should be very much greater. At the same time, the increased speed renders the planes more efficient, area for area, than the planes off the slower machine. 36 Natural stability in aeroplanes Chapter V. Variable speed and the parachute principle. Hitherto, on the score of efficiency and also of stability, our investigations have led us to seek for speed as the grand panacea. But there are usually two sides to question, and though, while in theory, speed may be most desirable, it becomes a source of considerable difficulty at both starting and landing. A machine built to fly at 80 miles per hour would have towed up something like 60 miles per hour below it could rise. And this difficulty is nothing like the problem that presents itself when we consider how it is stolen in safety from a flight at such a speed. It becomes evident that some provision must be made for starting and landing at some more practicable rates. We must have a variable speed machine. To convert a high-speed machine into low-speed machine means either variable surface area, variable camber, or variable angle of incidence. Any of these is possible, but the choice must be decided by simplicity of action. To spread extra wings when rising or landing is a cumbersome suggestion full of pitfalls, and liable to accidents through to failure of mechanics. Variable speed and parachute principle 37 call devices, which experience shows always have a way of failing at opportune moments. To vary the camber off the planes here, but having decided on using flat planes, it would be loss of strength to make these flexible and an increase of mechanical complications to have to flex them. It would be a zero alter thingly of incidence by having the leading edge capable of rotary movement, and machines have been constructed employing this principle. But the easiest planefall, since it does away with all moving parts whatever, would be told or not the planes themselves, but the whole machine. Thus suppose thingly of incidence, in order to an efficient lift, Tobe in 6, the lifting plane, along the same line, would be set in a chassis so that it percented anangly off in 5. The machine would then lift at a much slower speed. Actually, the tail being the furthest from the center of gravity would lift first, and as soon as the speed was sufficient, the pilot would alter the elevator, send down the tail on top the ground, thereby racing the leading edge off the front plane, and the machine would rise. As the speed increased, the tail would continue to rise, till at maximum speed the plane would beat the minimum angle with the horizontal, i.e. at its lowest angle of incidence. This solves the problem of starting, and to some extent off-landing. But we have not yet come to the end of resources. Most landings are effected by shutting off the engine and planing down. All flying machines will glide if you at the proper angle, and it 38 natural stability in aeroplanes is the business off the pilotot and tothus when he stops the engine. But to glide with the same wing area as used in flying means to glide at the same rate. In order to descend slowly, it is necessary to have more area. Is it possible to increase the area used for descent without interfering with the roast for flight? In the design we're engaged in considering, it is possible and without any mechanical devices. There is a large space between the front plane and the back plane which is at present unused. It is of very little value in flight, being an apteroid aspect and having practically no turning edge. But if the space is covered in it gives no resistance in flight, and in descent it becomes a very efficient parachute. Other than this, IF openings becute this plane immediately under the center of box skite ducts. The air under the longitudinal plane, having offered its resist ants to the vertical passage off that plane, will escape in the duct and again offer considerable resistance to the descent off thighs closed in surface before it escapes finally out of the duct. A model made on these lines will not need putting at an angle. Will assume its proper angle when left to itself by reason of its design and through weight is balanced between the supporting planes, and it will descend by partly gliding and partly parachuting at a step angle but quite slowly. While, if the pilot so choose, hecken, by racing the tail, increase the speed to glide, which can turn into a parachutation at any moment. 39 Chapter VI. The design which fulfills the conditions. In constructing any sort of machine, it is usual to first obtain the most important device and then to build up the accompanying parts to that. We have no succeeded in evolving the thing we look for, i.e., a plane which will fly and lift with the minimum off-head resistance, and which is absolutely stable laterally and longitudinally by reason of its construction and without any interference from the pilot or the employment of balancing devices of any description. We have no to fit the propelling apparatus, car, and chassis on tothas. Fortunately, the designation that lends itself easily to manipulation, which is not always the case with models. The short span off the planes, for instance, with the dihedral angle, a tone suggests girder construction, see Figs. 2930, which is perhaps the strongest of all devices, being an M-strut girder familiar to numberless bridges. The photo which forms the frontispiece of this book, and which, by the way, makes the car look much too large owing to its position nearest the camera, represents a 6-foot model which was exhibited at HE, or the Natural Stability in Aeroplanes Olympia show, in order to show the construction of a full-size machine made to the design of the paper model. This has since been considerably simplified, thought a broad line shave been retained, by doing away with the struts and supports at the rear. The whole off the back planes no supported by curved members, which start from the girder off leading edge and curve down to the T-section longi FIG. 29. Fig. 30. Udinals which form the rigid part off chassis. The cell longitudinals and the skids end at leading edge off the back plane and the laminated skids and wheels are placed there. The machine is built without a wire and without a casting. It was made entirely off wood, but is so designed that it can be made entirely out of steel tube using the ordinary screw connections. If built off timber, the joints are made with strips of steel bolted and screwed onto the wood. The girders forming the leading edge of fetch. Design which fulfills the conditions 41 plane have sockets formed in the upright struts of the minto which the ribs fit. See Fig. 30. And these are solid pieces one tapering to that railing edge, where they are clipped toes light spar which holds them toes there. This construction, while very strong is yet sufficiently flexible to be considerable before it reaches breaking point. Longitudinal rigidity secured by means off the triangular duct which forms a complete girder from intoned. A sufficient number of uprights fill the space between the plane and the T-section longitudinals which form the rigid bottom off the machine. On these latter the floor is placed and the car is built up, enclosing all the obstructions and putting the pilotina place off safety, enclosed on all sides in the middle of the strongest part of the machine, with the strongest portion of that part between him and the ground. The center of gravity is situated behind the pilot in the back of the car, near the floor, and her is space for the oil and petrol tanks. The engine is in front of the pilot, who is thus able to control it and watch it, and at his own time is free from the danger of having it fall upon him in case of an accident. As the machine turns horizontally and vertically on its center of gravity, the front part of the car forms a sort of baffle or blinker for the rudder and elevator to act against. Both these area that aloft the machine, where they have the most overage, and these two era-controlled Bythian lever, which is pushed forward or pulled backward to raise or lower the 42 natural stability in aeroplanes elevator, and turn it bicycle fashion to move the rudder. As the machine balances itself, there is no need for an balancing device either automatic or controlled. The propellers may bit more, and those in front find Dave from fixing in the intersection off to strong struts, which join the wingtips to the bottom off the car, and the supports which run from the center off these to the strong joint formed by the intersection of the longitudinal and lateral girder. At Heback there may be two propellers fixed as in the front, or own large one at her rear off the car. They are all worked from the one engine and the thrust is slightly above the center of gravity. Each propeller is placed just under the leading edge of Fig. 31 the Fig. 31. Idea being that a certain amount of air is always thrown out by centrifugal force all round a revolving propeller. And this air, which ordinarily is lost, must, when thrown upwards, exert a lift on the undersurface off the plane. Also, when thrown towards the car, it must, by impinging on the slanting surface off the car, tend to impel it forward. Fig. 32. Where four propellers are roost, the back pair should be of greater pitch than Zine, which fulfills the conditions 43 the front pair, as they must to certain extent work in this stream from the front pair. There are several ways of coupling the propellers to the engine. Butin the model they are shown coupled up by bolts, which seems to be the most efficient and lightest device. In order to cool the engine and keep the air in the car clear, a ventilating pipe is led from the front of the car to the engine, and the air rushing through Fig. 32. This at the speed off the machine, plays over the engine and is conducted out through a large opening and discharged at the back. The whole off this part of the machine is rigid and braced towards their bymeans off struts, though whether made off steel tube or timber, there must always, from the nature of the construction, be certain amount of elasticity which makes for strength, agrate. 44 natural stability in aeroplanes advantage over a construction braced rigidly by non-elastic wires, which snap instead off jiving to sudden strain. Under the too rigid T-section, longitudinals their area number of plastic laminated wood spring set at an angle, and the lower ends of these aeropivoted onto long elastic skid. This skid is made in laminations, with alternate joints, and starts from the point where the two planes intersect in front of the machine, which is sewn off the strongest joints in the whole construction. From this point it bends out in a semicircle to protect the propeller and the front of the machine and car, this portion of it being very elastic by reason of the laminations, having free play one upon the other. At head bottom off the semicircle, the skid is joined to the slanting skids or springs, depending from the bottom of the machine. And her the laminations are bolted together making the skid stiffen. The skid runs the whole length off the machine like the runner off a sledge. On the skid, the wheels are sprung with a steel springover arrangement. Fig. 33. The shock offlanding is, therefore, taken first on the wheels, and should it sufficient lie heavy tacos the skids to touch the ground there is still the series off laminated wood springstow, absorb any vibrations, and prevent any possible shock to the car. The car is so secure from vibration by reason of the set precautions that the whole lower half off the front of it may be made of protected glass, to enable the pilot to take clear view of his surroundings. Design which fulfills the conditions 45. 46 natural stability in aeroplanes. The dimensions of full-sized machine are estimated to as follows: span 20 feet length, 43 feet per shooting area, 500 square feet efficient lifting area, 360 square feet weight, a lup, 800 ib. It will be understood that though only 360 square feet is counted as sufficient for lifting, the whole 500 square feet is sufficient as parachuting surface in descending. Weight off the machine compares very favorably with existing machines, and the load 2 j-ibs per square foot gives plenty off margin for passenger carrying. The chief advantages claimed for this machine are 1. Speed, 2. Stability, 3. Strength of construction, 4. Shock-absorbing capacity. It is a practical impossibility for the machine to turn over or be blown over, and it will recover its balance if started at any angle. If a load taught vertically, either tail first or head first, it will recover its position in 6 times its own length, purely by its own balance, without any effort off the pilot. London, printed by William Clowes and Sons, Limited, Great Windmill Steke, W. Anjuk Street, Stamford Street, S.E. Page 51, page 52, S&C, list January 1912. A complete list of the books included in the S&C series of elementary manuals for mechanics and students published by E&F Spawn Limited, London. The S&C series uniform in cloth prices, 6D, Netty. 1. Modern primary batteries by X.H. Schneider. 2. How to install electric bells, annunciators, and alarms by N.H. Schneider. 3. Electrical circuits and diagrams, Part I by N.H. Schneider. 4. Electrical circuits and diagrams, Part Roman II by N.H. Schneider. 5. Experimenting with induction coil by N.H. Schneider. H.S. Norrie. 6. Study of electricity for beginners by N. H. Schneider. 7. Dry batteries, how to make and use them, by a Dribbery expert. 8. Electric gas lighting, by N. H. Schneider. 9. Model steam engine design, by R. M. Devignier. 10. Inventions, how to protect, sell, and buy them, by F. B. Wright. 11. Making wireless outfits, by N. Harrison. 12. Wireless telephone construction, by N. Harrison. 13. Practical electrics, universal handybook on everyday electrical matters. 14. How to build a 20-foot biplane glider, by A. P. Morgan. 15. The Model Vaudeville Theater, by N. H. Schneider. 16. The Fireman's Guide, a handbook on the care of boilers, by K. P. Dahlstrom. 17. A. B. C. Off the steam engine with a description off automatic governor, by J. P. Lisk. 18. Simple soldering, both hard and soft, by E. Thatcher E. and F. N. Spawn Limited, London. The S&C series uniform in cloth prices, 6D net each. 19. Ignition accumulators, their carry and management, by H. H. U. Cross. 20. Key to linear perspective, by C. W. Diamond. FSA. 21. Elements of telephony, by Arthur Crotch. 22. Experimental study off gyroscope, by V. E. Johnson. M.A. 23. The Coreless Engine, by J. T. Henthorne. 24. Wireless telegraphy for intending operators, by C. K. P. Eden. 25. Wiring houses for the electric light, by N. H. Schneider. 26. Low-voltage electric lighting with a storage battery, by N. H. Schneider. 27. Practical silo construction in concrete, by A. A. Houghton. 28. Molding concrete chimneys, slate, and roof tiles, by A. A. Houghton. 29. Molding and curing ornamental concrete, by A. A. Houghton. 30. Concrete wall forms, by A. A. Houghton. 31. Concrete monuments, mausoleums, and burial vaults, by A. A. Houghton. 32. Concrete floors and sidewalks, by A. A. Houghton. 33. Molding concrete bathtubs, aquariums, and natatoriums, by A. A. Houghton. 34 to 38 inclusive. Works on concrete structures, by A. A. Houghton and N. Cohenth Press. 39. Natural stability and the parachute principline aeroplanes, by W. Lemaitre. 40. Builders' quantities, by H. M. Lewis E. and F. N. Spawn Limited, London. A2. No asterisk L. The S and C series, price 1/6 net modern primary batteries. Their construction using maintenance, including batteries for telephones, telegraphs, motors, electric lights, induction coils, and for all experimental work, by Norman H. Schneider. 55 illustrations and 94 pages of text. No. 2. The S and C series, price 1/6 net, how to install bells, annunciators, alarms, including batteries, wires and wiring, circuits, pushes, bells, burglar alarms, high and low water alarms, fire alarms, thermostats, annunciators, and the location and remedying off troubles, by Norman H. Schneider. 59 illustrations and 68 pages of text. No. 3. The S and C series, price 1/6 net. Electrical circuits and diagrams illustrated and explained. Part I. New and original drawings comprising alarms, annunciators, automobiles, bells, dynamos, gas lighting, motors, storage batteries, street railways, telephone, telegraph, wireless telegraphy, wiring, and testing, by Norman H. Schneider. No. 4. The S and C series, price 1/6 net. Electrical circuits and diagrams, Part Roman II. Alternating current generators and motors, single-phase and polyphase transformers, alternating current and direct current motor starters and reversers, arc generators and circuits, switches, wiring, storage, battery meter connections, by Norman H. Schneider. No. 5. The S and C series, price 1/6 net. Experimenting with induction coils, containing practical directions for operating induction coils and Tesla coils, also showing how to make the apparatus needed for the numerous experiments described, by H. S. Norrie, author of Induction Coils and Coil Making. 26 illustrations and 73 pages of text. No. 6. The S and C series, the price 1/6 net. Study or electricity phobogeners, comprising the elements of electricity and magnetism as applied to dynamos, motors, wiring, and toll branches of electrical work, by Norman H. Schneider, with 54 original illustrations and 6 tables. No. 7. The S and C series, price 1/6 net. Dry batteries especially adapted for automobile, launch, and gas engine work, medical coils, bells, annunciators, burglar alarms, telephones, electrical experiments, and all purposes requiring a good battery, with 30 original illustrations. H. Iflash lamp Idrisel. No. 8. The S and C series, price 1/6 net. Electric gas igniting apparatus, how to install electric gas igniting apparatus, including the jump spark and multiple systems for all purposes, with suitable batteries and wiring, by H. S. Norrie, author of Induction Coils and Coil Making / No. 9. The S and C series, price 1/6 net. F.L. Odell Steam Engine Design A Handbook for the Designer of Small Steam Engines, by R. M. Devignier, including original tables and calculations for speed, power, proportions off pumps, compound engines, and valve diagrams. 34 illustrations and 94 pages of text. No. 10. The S and C series, price 1/6 net. Inventions, how to protect, sell, and buy them, by. Write 118-page soft text. No. 11. The S and C series. Price 1/6 net. Making wireless outfits concise and simple explanation on the construction and use of inexpensive wireless equipments up to 10 miles by Newton Harrison, EE with 27 illustrations and 61 pages of text. No 12, the S and C series. Price 1/6 net. Wireless telephone construction, a comprehensive explanation of making OFA wireless telephone equipment for receiving and sending stations, with details of construction by Newton Harrison, EE with 43 illustrations and 74 pages of text. F transmitting station, D receiving station. No 13, the S and C series. Price 1/6 net. Practical Electrics, a universal handy boo on electric bells, batteries, accumulators, dynamos, motors, induction and intensity coils, telephones, microphones, phonographs, photophones, etc. with 12 asterisk illustrations and 135-page soft text. No 14, the S and C series. Price 1/6 net. How to Build a Biplane Glider, a practical handbook on its construction and use by Alfred Powell Morgan, illustrations and 60 pages of text. No 15, the S and C series. Price 1/6 net. Vaudeville Theater's Norman H. Schneider with 34 illustrations and 90 pages of text. No 16, the S and C series. Price 1/6 net. The Fireman's Guide and Handbook on the Carafe Boilers by Carl P. Dahlstrom, MEB2. No 17, the S and C series. Price 1/6 net. ABC off the steam engine and automatic governor, 6-scale drawings of a high-speed steam K-engine and automatic governor. Each part is given in detail with its name and number, Forsey reference with description, with a chapter on lubrication and other practical information. By J. P. Lisk, M.E. No 18, the S and C series. Price 1/6 net. Simple soldering, both hard and soft, together with descriptions of inexpensive home-made apparatus necessary for the art. By Edward Thatcher, instructor of decorative metal work, Columbia University, New York, 52 illustrations and 76 pages of text. No 19, the S and C series. Price 1/6 net. The Carrion Management OP ignition accumulators and electric light, 4 million, containing practical information on charging and repairing of motorcycle, motorcar, and other similar ignition accumulators. Also, the adaptation of a slightly larger genus to unique system of electric lighting by Harold H. U. Cross/2 illustrations and 66 pages of text. Contents: the charging of accumulators, the repairing of accumulators, the accumulator in the home. No 20, the S and C series. Price 1/6 net. A Key Theory and Methods of Linear Perspective by Charles W. Diamond, FSA, with 16 illustrations in 6 plates and 32 pages of text. Theme of the author of this brief treatise has been to include within the smallest possible compass everything that is required to convey to reader, whose time is limited, a competent knowledge of the theory and the rudiments of the practice of drawing in perspective. No 21, the S and C series. Price 1/6 net. Elements of Telephony by Arthur Crotch, silver medalist and honorsman in telegraphy and honorsman in telephony, City and Guilds of London Institute, sometime lecturer in the subjects at Municipal Technical Schools, Norwich, with 51 illustrations and 90-page soft text. No 22, the S and C series. Price 1/6 net. The Gyroscope, an experimental study from spinning top to monorail by V.E. Johnson, M.A. author of The Theory and Practice of Model Aeroplanes, formerly exhibitioner of Magdalene Call, E. Cambridge, with 34 illustrations and 40-page soft text. No 24, the S and C series. Price 1/6 net. Operator's Handbook of Wireless Telegraphy, a simple treatise upon the theory and working of commercial wireless telegraphy for the assistance of intending wireless operators by C.R.P. Eden, B.Sc., etc. Consulting engineer for wireless telegraphy installations, also electrotherapeutic and radiography specialist. In press, contents: detectors, transmitters, tuning apparatus, wireless station equipment, aerials, and Earth's small power experimental apparatus. No 25, the S and C series. Price 1/6 net. Wiring houses, the electric light, Norman H. Schneider, with 44 illustrations and 86 pages of text. No 26, the S and C series. Price 1/6 net. Low voltage electric lighting with the storage battery, specially applicable to country houses, farms, small settlements, yachts, etc. By Norman H. Schneider, 23 illustrations and 85 pages of text. No 27, the S and C series. Price 1/6 net. Practical silo construction advertise, illustrating and explaining the most simple and easiest practical methods of constructing concrete silosoffel types with unpatented forms and molds. The data, information, and working drawings given in this book will enable the concrete builder to successfully construct any of the most practical types of concrete silos in use today by A. An author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 18 full-page illustrations. The Norman W. Henley Publishing Co. E and F. N. Spawn Limited, 57 Haymarket 1911. No, 28. The S and C series. Price 1/6 net. Molding concrete chimneys, slate and roof tiles. A practical treatise explanatory of construction of block and monolithic types of concrete chimney with easily constructed molds for same. The construction of monolithic concrete roofs, also the molding of concrete slate, roof tile sand slabs, artfully treated by A. Houghton, author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 15 full-page illustrations. Mu. The Norman W. Henley Publishing Co. H. Schonben E. and F. N. Spawn Limited, 57 Haymarket 1911. No, 29. The S and C series. Price 1/6 net. Molding and curing ornamental concrete. A practical treatise covering the various methods of preparing the molds on a filling with a concrete mixture, remedying defects in the cast, surface treatment for various effects, the proper proportions and preparation of concrete, and the best methods of thoroughly curing the work by A. Houghton, author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 5 full-page illustrations by the Norman W. Henley Publishing Co. E and F. N. Spawn Limited, 57 Haymarket 1911. No, 30. The S and C series. Price 1/6 net. Concrete wall forms. A practical treatise explanatory of the construction of all types of wall forms, clamps, separators, and spacers for reinforcement. Full details and working drawings of an automatic wall clamp are given, with the operation of same onal styles of walls. Foundations, retaining walls, placing floor joints, molding water tables and window lodges, as well as molding fireproof floors and preparing foundations for concrete walls. Aerial soffiliated A. Houghton, author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 16 full-page illustrations by J. Ott. The Norman W. Henley Publishing Co. E and F. N. Spawn Limited, 57 Haymarket 1911. No, 31. The S and C series. Price 1/6 net. Concrete monuments, mausoleums, and burial vaults. A practical treatise explanatory of molding of various types of concrete monuments with the construction of molds for same. Lettering and ornamental effects with simple methods of securing the desired results artfully. Plans and designs for mausoleums and burial vaults are given, with complete details of construction by A. Houghton, author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 18 full-page illustrations. The Norman W. Henley Publishing Co. Anton E. and F. N. Spawn Limited, 57 Haymarket 1911. No, 32. The S and C series. Price 1/6 net. Concrete floors and sidewalks. A practical treatise explaining the molding of concrete floor and sidewalk units with plain and ornamental surfaces, also the construction of plain and reinforced monolithic floors and sidewalks. Complete instructions are given for all classes of this work, with illustrations of the easily constructed molds for diamond, hexagonal, and octagonal floor tile by A. Houghton, author of Concrete from Sand Molds, Ornamental Concrete Without Molds, etc., etc. 8 full-page illustrations. The Norman W. Henley Publishing Co. Lonben E. and F. N. Spawn Limited, 57 Haymarket 1911. No, 33. The S and C series. Price 1/6 net. Molding concave bathtubs, aquariums, and natatoriums. A practical treatise explaining the molding in concrete of various styles of bath laundry trays, etc., with easily constructed molds for the purpose. 7. He molding of aquariums and natatoriums, as well as the waterproofing methods used for same, artfully by A. Houghton. 16 full-page illustrations. The Norman W. Henley Publishing Co. Zonben E. and F. N. Spawn Limited, 57 Haymarket 1911. No, 39. The S and C series. Price 1/6 net. Natural Stability and the Parachute Principle in Aeroplanes by W. Lemater Hahn, Sec. Aeroplane Building and Flying Society, with 34 illustrations, /F tilde7, and 48 pages of text preface. The importance of stability. Speedasa, means of stability. The low center of gravity, short span and area, variable speed, and the parachute principle, the design which fulfills the conditions. No, 40. The S and C series. Price 1/6 net. Builders Quantities by Horace M. Lewis, Associate Institution, Odge Municipal and County Engineers, member of Royal Sanitary Institute, lecturer on Builders Quantities. Pool School Technology, Contents General Introduction, How to Measure Areas. Worked examples, methods of measurement. Excavator, sewers and house drains, bricklayer, reinforced concrete, mason, slater, slate mason, tiler, stone, tiling and slating, plasterer, carpenter, joiner, and ironmonger, smith, and founder, hot water system, lighting, bells, plumber, painter, glazier, and paper hanger. Examples of billing. With 6 illustrations and 54 pages of text, This work is intended togavenial mentary knowledge of subject of builder's quantities. Tomit thuant for a sheep yet reliable handbook. Within thereach ofri building student and all engaged in the building trade. With this recanion connected with the trade can measure up efficiently according to the customary methods of measurement in the London Standard. Yes and C series uniform in cloth prices. 6D Netty. 1. Modern primary batteries by N.H. Schneider. 2. How to install electric bells, annunciators, and alarms by N.H. Schneider. 3. Electrical circuits and diagrams Part I by N.H. Schneider. 4. Electrical circuits and diagrams Part Roman II by N.H. Schneider. 5. Experimenting with induction coils by N.H. Schneider. H. S. Norrie. 6. Study of electricity for beginners by N.H. Schneider. 7. Dry batteries, how to make and use them by a tributary expert. 8. Electric gas lighting by N.H. Schneider. 9. Model steam engine design by R.M. Devignier. 10. Inventions, how to protect, sell, and buy them by F.B. Wright. 11. Making wireless outfits by N. Harrison. 12. Wireless telephone construction by N. Harrison. 13. Practical electrics. Universal handybook on everyday electrical matters. 14. How to build a 20-foot biplane glider by A. P. Morgan. 15. The Model Vaudeville Theater by N. H. Schneider. 16. The Fireman's Guide, a handbook on the care of boilers by K. P. Dahlstrom. 17. ABC. Off the steam engine with a description of automatic governor by J. P. Lisk. 18. Simple soldering, both hard and soft by E. Thatcher E. and F. N. Spawn Limited, London. Yes and C series uniform in cloth prices. 6D net each. 19. Ignition accumulators, their carry-in management by HHU Cross 20 Key to Linear Perspective by C.W. Diamond. FSA 21 Elements of Telephony by Arthur Crotch. 22. Experimental Study of Gyroscope by V.E. Johnson. M.A. 23. The Coreless Engine by J.T. Henthorne. 24. Wireless Telegraphy for Intending Operators by C.K.P. Eden. 25. Wiring Houses for the Electric Light by N.H. Schneider. 26. Low-voltage electric lighting with a storage battery by N.H. Schneider. 27. Practical silo construction in concrete by A.A. Houghton. 28. Molding concrete chimneys, slate, and roof tiles by A.A. Houghton. 29. Molding and curing ornamental concrete by A.A. Houghton. 30. Concrete wall forms by A.A. Houghton. 31. Concrete monuments, mausoleums, and burial vaults by A.A. Houghton. 32. Concrete floors and sidewalks by A.A. Houghton. 33. Molding concrete bathtubs, aquariums, and natatoriums by A.A. Houghton. 34 to 38 inclusive. Works on concrete structures by A.A. F. Faugton and now in the press. 39. Natural Stability and the Parachute Principline Aeroplanes by W. Lemaitre. 40. Builder's Quantities by H. M. Lewis E. and F. N. Spawn Limited, London. Page 93. University of California Library. Berkeley S. Book is due on the last date stamped below. Books not returned on time. Ara subject to fine off 50 C per volume after the third day overdue, increasing to $1.00 per volume after the 6th day. Books note in demand may be renewed if application is made before expiration of loan period. Oct 150 M7, 27. IB University of California Library. Page 96.